Swayam Prabha. Digital India. Educated India.
Hello, good afternoon. So, welcome to the course on comprehensive view of speech processing, and today's lecture is 19th in series. So, today we are going to discuss about the linear prediction analysis applied to speech. So, this topic we have started in the last class, and today we are continuing that. So, the linear prediction analysis is particularly very much applicable to the speech due to the following reasons. You can see that the linear prediction analysis, because as you know that the speech signal is a correlated one, highly correlated one. It means the samples, if you observe the relations between the samples in a speech signal, they have a higher correlation, because the speech signal is produced from a physical system, the oral cavity and the vocal tract system. So, the acoustic signal that is emitted from that bears the correlations among the samples and all. So, that is the reason that when you are applying the LP analysis to the speech, so this all pole model of LPC can provide a very good approximation to the vocal tract spectral envelope of a quasi steady state voice regions, because in a voice regions the vocal tract will be widely open and it will be excited by the periodic pulse train. So, you can able to see the correlations between the samples at very high during that voice region. So, therefore, it can be very much better modeled by using the all pole model of a LPC. And but at the same time, as I mentioned that, so the unvoiced and transition regions of a speech are not that good, or not that much effectively modeled by the LP analysis, because the reason is that in the unvoiced segments of a speech or transition segments of a speech, where the basic excitation itself is a noisy excitation, like opening the constriction and the turbulence of air is passing through narrow constriction. So, all these modes of excitation that gives you like noise like characteristics. So, therefore, the resultant acoustic signal is also noisy, and as we know that in the noisy signal the correlations are very less. So, therefore, the LPC, the modeling with the LPC linear prediction analysis during these segments will be not a very good approximation and all, but still as you see in a totality, where most of the speech will be like the voiced segments of speech. So, therefore, on overall, so the LP analysis will provide a good model for the speech analysis. And other one is that using LP analysis you can able to separate the source and system, because as we know that the acoustic signal that is emitted from the mouth or emitted from the oral cavity, it is a combination of both the vocal tract response and as well the excitation signal also. And so it's like the combined signal, or like the signal having the presence of both the characteristics will be present in the speech signal and all. And for certain applications, actually, if you want to discriminate the sounds, if you have excitation characteristics, you can able to discriminate better, and whereas for certain sounds the vocal tract characteristics are better, or the best source of will provide the better evidences, so that instead of extracting the features directly from a speech, if you can split the speech, or if you can able to separate these vocal tract and the excitation components, and we can use these components separately for discriminating either the sound units or discriminating the speakers or languages, that can be done very effectively. And later we can fuse the confidences offered by both the components also, so that the effective performance will be improved. And then another one is that the LPC is analytically tractable model. It means because it is mathematically precise, you can see that when you are modeling the signal with LPC, you can clearly see that it is completely tractable mathematically analytically, and so that the implementation of this model will be very easy by using either software or hardware, and computationally also it is efficient when you compare with the existing model at that point of a time, that is a filter bank analysis and all. Compared to that, the LP analysis will be computationally very efficient, and also that the LPC model found to be like working well or found to give a better results compared to the existing systems, that is mainly the filter bank analysis and all at that particular point of a time. So, because of these positive aspects, the LP analysis has been very extensively used in 60s, 70s and even till 80s also. So, basically the application that was used at that particular point of a time will be for a telephonic application, that is for speech transmission through the telephonic channels and all. So, at that time the ultimate goal is that effective representation of a speech or effective representation of a speech, so that that means effectively you can able to represent the speech with a lesser number of bits, so that you can effectively utilize the bandwidth that is offered by a channels and all. So, that way in the context of speech coding, this LP analysis has been used till 70s, right. And after that, since this LP analysis has been very much analyzed by a lot of researchers and all, so the whatever the features are that are derived by using LP analysis have been also explored later on for other speech tasks like speech recognition, speaker recognition, language identification and different aspects of various speech tasks. So, in last class we just briefly discussed about this. So, in the LPC model, the basic idea here is that since the samples are correlated, so we can predict the sample, the present sample from the knowledge of its previous samples. So, here suppose for example, so if you want to predict or if you want to predict the nth sample, you can able to predict the nth sample based on the observation of the a set of previous samples. So, here you can see S of n minus 1, S of n minus 2, S of n minus p. So, these indicates the previous samples. S of n minus 1 means it is just previous sample, and n minus 2, n minus 3, n minus p means it is like a pth previous sample with respect to the present sample. So, here in the linear prediction analysis, here based on the knowledge or based on the information based on the previous samples, you can able to predict the present sample. So, here you can see that we are predicting the present sample as a linear combination of the previous sample, some p previous samples. P is a number like p previous samples, the p may be 10 or 20 like that. And here this is a linear combination, and then this is a weighted linear combination. You can see we are scaling each of the previous sample by different constants like A1, A2, A3, AP and all, right. And so, since these are the scaling constants or the scaling factors for the previous samples. So, and here you can see we have this S of n minus 1, S of n minus 2, S of n minus p are available, and with these previous samples we are predicting the present sample. And for that what we are doing, we are performing the weighted linear combination of the previous samples, and for these A1, A2, A3, AP, they are providing the scaling factors or weighting factors and all. And so, with that we can able to approximate or we can able to predict the nth sample. But this is approximation, right, because the actual S of n may have some certain value, and based on the previous samples we are predicting the present sample. So, that gives you the approximation. There will be some difference will be there, it is not exactly the same of the present sample and all. So, therefore, that is the reason that this S of n we are making as approximately equal to approximation of the previous samples, right. So, if you want to remove this approximation, then we will add the appropriate term as here to this approximation, then we can make it equal, right, we can make it equal. Then this gives you the linear prediction model, where you can say that this S of n is a combination of this is a predicted term, like this gives you the prediction of the S of n, and then this is the input, this is the some added input, so that this S of n, the actual input is equated to the predicted signal or predicted the input, the predicted the sample versus some input. So, this is here, this is G is known to be the gain of the excitation, since this is the input, and U of n is the normalized excitation. And now, if you write this in the form of system of equations, so we need to apply a Z transform on this. So, if you apply Z transform, this expression becomes this way: S of Z, and this S of delayed samples, if you apply S of Z, it is nothing but Z power minus I, whatever the delay, into S of Z, right, and this is G into U of Z, and you have expression in Z, right. Now, here we can rearrange the terms, and you can able to compute the transfer function of a system where H of Z is nothing but S of Z by G into U of Z. So, the transfer function of a system is nothing but you have a system, and whatever the numerator is nothing but this is the outcome of a system, and whatever the denominator is nothing but this is the input of a system and all. So, that way, by knowing this, you can see by doing this we can able to see here the transfer function appears to be like it is a polynomial of Z in the denominator. So, since there is no Z terms in the numerator, so we can call this transfer function or a system function as a all pole system, or the system can be viewed as a all pole system, because there is no expression or like no polynomial in the numerator. So, therefore, whatever the system characteristics, that basically depends on the expression, or you can say that the polynomial in the denominator and all. So, by solving this polynomial we can get the roots of a polynomial, and at the root locations, like if you apply at the root locations, this particular system will provide the response of infinite and all, because at root locations means then this polynomial will give you the 0 in the denominator, value 0 in the denominator. So, 1 over the 0, that means you will get infinite, the response will be peaks up. So, therefore, the root locations or the roots of this polynomial are known to be the poles of a system, right, and since only the poles are available for this system, so this system is known to be all pole system and all. So, it is I think about 1 by A of Z. So, now you can able to write this in the form of this system representation. You can see this is 1 by A of Z is the transfer function of a system. It should have some output and input. So, what is the output? Output is S of Z. So, therefore, this is the output, like in the time domain this is nothing but S of n, right, or in the Z domain this is S of Z, and the input is G into U of Z. It is nothing but U of n is the normalized excitation, and the G is the appropriate gain for the corresponding excitation and all. So, this is the product of these two that gives you G into U of n, and this is a system transfer function, and this is the outcome of that, right. And now, you can see in this system, the system output is a speech signal. It means that the system generates the speech signal. So, therefore, this LPC model corresponds to, or also known as speech synthesis model, because we are synthesizing the speech. That means, the outcome of the speech, the outcome of this particular system is a speech signal S of n. The outcome of this signal is a speech signal S of n, right. And so, this is the input, So, it is nothing but the excitation. We know that the speech is produced by like a time varying excitation exciting the vocal tract system, and now this block can be viewed as a vocal tract system or a vocal tract filter, right. In in the digital domain you can call it as vocal tract filter, and this filter is excited by input, like this is the excitation signal, and the output will be the speech, signal or acoustic signal. And now, since this is a vocal tract filter, and since it is all pole filter, so if you want to analyze this vocal tract filter response, right, if you want to analyze the vocal tract filter response, then what you can do, you can able to compute you can able to find out like here Z is nothing but e power j omega, and then by varying different values of omega, and if you can able to compute this 1 over a into e power j omega, and if you plot those values, then you can able to get the response of the system, or you can say that the response of the vocal tract filter. And as you know that in the response of the vocal tract filter, you can see if you take directly 1 over e power j actual magnitude or absolute magnitude, if you plot it, you can able to see that the characteristic, that means the low frequencies having very having lot of energy, or the most of the energy is considered or will be concentrated in the low frequencies, and the other frequencies or the higher frequencies, the energy that is concentrated or energy that is represented by the other frequencies are very, very less. So, if you want to, if you visualize, if you directly plot the absolute magnitude response of a filter, you may not see the details of the other frequencies, because only the most of the energy or 95% or 99% of the energy is mainly contributed by the low frequencies, or very few set of frequencies, right, and the remaining energy will be focused by the other frequencies. So, therefore, you cannot visualize that the response or the energy that is present in the other frequencies. So, therefore, to visualize that, we are using in the logarithmic scale, like we are taking the log magnitude, log absolute magnitude, then you can able to see that, because the log absolute magnitude on this scale you can able to see the energy distribution over the frequencies and all. And since it is all pole filter, you can able to see that at the pole locations. So, here you can see the peaks of these characteristic, peaks of this frequency response corresponds to the poles. That means, at this position we have the poles may be present. So, during the pole location, the system response will be peaks, will be very high, will be moved towards infinite and all. So, therefore, these are the places where the poles are existing in the system. That means, these poles are offered by this particular polynomial and all. So, therefore, you can able to see the sharp rise in the frequency characteristic that is offered by this all pole system. So, this we come across when you are discussing about the poles and zeros of a system. At that time, we have clearly seen that. So, in case of poles, how the response will be, and in case of zeros, what will be, how the response used to be, right. And so, now if you look at the same thing, the same system. So, for a speech synthesis model, we know that. So, this is your vocal tract filter, and whose response is 1 by A of z all pole filter, right. And then the input to this vocal tract system will be the excitation, and this is G into U of n. So, G is the gain, and this excitation will be, again there are two types, that depending upon the speech segment. If the speech segment that need to be produced is a voiced speech segment, then the excitation will be offered by the vocal folds, basically. And if the speech segment that need to be produced is unvoiced, then the excitation will be offered by some noise source, and that will be generated by different means, because this noise source will be generated by either blocking the vocal tract at different places, and then sudden release of that blocking, that gives you that provides the excitation and all. So, that way the unvoiced stops, consonants, all of them are produced by that kind of excitation, because where during exhalation process the vocal tract will be closed, and then the pressure will build up, and then when the pressure reaches to a particular threshold, then the constriction or the block or the blockade, whatever we applied, so that will be released. Because of sudden release, you have air will be rushed through that, and that provides in the form of turbulence of air, and that gives you a noisy excitation. This is one type of excitation. There are other excitations, as we know that in case of fricative sounds, like for example sa, sa, sha. So, for all of them the excitation is also noisy, but that excitation, in that case the excitation will be produced by a narrow opening during the blocking process, whereas for unstopped stop consonants, right, the blocking will be complete. That means, we will block or we will close the vocal tract completely, there won't be any leakage of air at all. And whereas in case of fricatives, we will try to block the vocal tract like at a particular place, but when you are trying to block, there will be some narrow opening will be there. So through that narrow opening, the air will be pushed, air will be rushed through that. So that acts as excitation, that is unvoiced excitation. So these unvoiced excitations will be modeled by using a random noise generator, right? And whereas for periodic excitation, that will be modeled by using the impulse train or the sequence of pulses, right? And so that way, based on the segment, whether it's a voiced segment or unvoiced segment, so here we have a switch, and that switch will be connected to one of these two excitation sources. Either voiced means it's like a pulse train, and for unvoiced it is connected to the random noise generator. And in case of voiced excitation, we know that there is a pulse train, but the periodicity of a pulse train has to be specified. It is going to be pitch period, because suppose you want to generate the voice corresponds to the man, right? So his pitch will be different from a female speakers. Likewise, the children's speech, where their pitch will be different. So therefore, depending upon requirement, we need to specify the pitch period, or the spacing between the impulses has to be specified. So therefore, so that way the excitation can be parameterized based on these things, whether the segment is voiced segment or unvoiced segment. If it is a voiced segment, what will be the pitch, right? What will be the pitch period, right? Spacing between the pulses. So these are the things that need to be informed with respect to, that need to be provided with respect to the excitation, right? And along with that, for every segment, we need to mention about what is the gain, what will be the gain, right? So these are the, with respect to excitation, so these are the three parameters that need to be specified. One is the gain of the segment, and other one is that whether the segment to be synthesized or segment to be like the speech need to be generated, the segment will be whether it's a voiced or unvoiced. If it is a voiced, then we have to specify the pitch period and all, right. So these are the three parameters that that together represents the excitation and all. So then after the excitation, then we need to also parameterize the vocal tract system. So this vocal tract system is nothing but represented by 1 by A of Z, and this A of Z is nothing but like, it's nothing but a polynomial of a Z with the previous samples and all. And along with that, we have some scaling factors are there, or the constants, scaling constants. So these scaling constants are nothing but A1, A2, A3 up to AP, right. So here this vocal tract system is nothing but like finding or determining those the weighting factors or the scale factors or coefficients, constants like A1, A2, A3, AP. Like, so that way this vocal tract system is represented by some set of coefficients, some set of constants or coefficients, right. So the for example, here suppose we are representing we are estimating the like we are predicting the sample with the P previous sample, then the P will be the number of coefficients, the P is that number, right. The P may be 10 or 15, something like that. So here the vocal tract system or vocal tract filter is nothing but those that is nothing but like finding that optimal set of coefficients, right, the P coefficients that corresponds to the vocal tract system and all. So once we have that, right, then we can able to generate the speech, right. So for every speech frame, we need to know about what is the segment type, whether it's a voiced segment or unvoiced segment. If it is a voiced segment, then we need to specify the pitch period, and then for that particular segment we also specify the gain, and then for that particular segment we need to specify the set of coefficients, because the speech is a time varying signal, right. So therefore, for every frame, for every the 20 milliseconds or 30 milliseconds which we considered during that time, the speech have the stable characteristics. So during that interval, like we need to specify the vocal tract characteristics also. So how do you specify the vocal tract characteristics? The vocal tract characteristics are specified by that set of coefficients, the P coefficients. So that way, in case of speech synthesis model under the LPC model, where we will parameterize the speech every frame using these three parameters corresponds to excitation, and then a p parameters corresponds to the vocal tract system. So, that way every frame will be represented by these parameters and all these parameters. Suppose a speech signal for every 5 milliseconds, if you have a frame of 20 milliseconds, means suppose a speech of 1 second means we have 200 frames. So, every frame has to be represented by these parameters and all has to be represented by these parameters. So, that way from the input side the speech signal will be coded by using these parameters, like for every 5 milliseconds we have a speech frame, and for that speech frame will be parameterized by this one, whether it is a voiced or unvoiced frame. For that parameterization 1 bit is sufficient, right, and if it is a voiced frame, then we need to provide the pitch. So, pitch is again it is a integer quantity, like that it is varying from like for example is a number varying from like 50 to go up to 500 for example. So, we need to represent, so for that it requires a certain number of bits, and then the gain. So, for gain also we require we need to quantify that. So, therefore, for encoding that we need certain number of bits, and then here we have some coefficients, some number of coefficients. For each coefficient, for coding that for representing that we need certain number of bits. So, that way if you add up all of those bits, that gives you the what is the how many bits that are required to represent a speech frame and all. And we have in 1 second, as I mentioned, that we have about 200 frames. So, therefore, whatever the number of bits that are required per frame, and if you multiply with the 200, that gives you the total number of bits that are required for representing a speech. So, that way we can encode the speech using the LP analysis and all. And now we will see that how do we know that actually here these filter coefficient, how do we estimate the filter coefficients. So, that is nothing but the LP analysis. In the analysis process we can come to know that what are the optimal coefficients that represents the particular speech frame. Yeah. So, this is the analysis phase, and so the previous one is the speech synthesis one. So, where you can see that in the model, in the speech production model, you have a excitation as input and you have a vocal tract system, right, and output will be the speech. And now here you can see this is a speech analysis model. So, in this analysis model we will see that, so we know that S hat of n is nothing but it is a predicted speech sample, predicted nth speech sample. So, for predicting the nth speech sample, you can able to predict from the history, from your past p samples. So, here you can see S of n minus I, it is nothing but the previous ith sample with respect to the n, right. And now here we are considering the history up to p, some number of p samples. So, I equals to 1 to p, where I equals to 1 gives you the just previous sample, one sample previous to the nth sample, that is n minus 1. I equals to 2 means n minus 2, that is the second previous sample. Likewise, we consider the p previous samples, and here the linear combination, or you can say that the weighted linear combination of the previous p samples, it provides you the predicted sample, the predicted value of the nth sample, right. So, therefore, S hat of n is nothing but the predicted signal, and my S of n is the actual signal, S of n is actual signal. So, the difference between these two sample values, it gives you the error in prediction. That means E of n is nothing but error in prediction of the nth sample, because we know that S of n is the actual sample value and S hat of n is the predicted value, right. The difference between these two give you the error in prediction of the nth sample. So, this is nothing but S of n minus S hat of n. We know that S hat of n can be obtained from the previous p samples, like this way, summation of the weighted linear combination of that. So, therefore, S of n minus the summation of these previous samples, it gives you the error in the prediction, error in the prediction. So, now you can see this is the error in the prediction, and so therefore, just for this expression, if you apply the jet transform, then you can see that E of n is nothing but S of n minus S hat of n, right. S hat of n can be written as this way, the summation of the previous samples weighted by some weighting coefficients and all, right. Here our goal is that in the analysis phase, our aim is that this E of n has to be minimized, because the error, that means we need to perform a prediction more accurately such that the difference between the actual signal and the predicted signal should be 0 in ideal case, but it cannot happen that, right. So, therefore, we will try to minimize this E of n for the entire frame, because the frame contains 20 milliseconds, and suppose if the sample is if the signal is sampled at 10 kilohertz or 10,000 samples per second, then this 20 milliseconds contribute to 200 samples. So, for every sample we will try to see what is the prediction error and all, and then here our goal is that we need to minimize this prediction error for the total frame, right. So, this is the objective here in the analysis model, and now here we will take for representation of the system in analysis model, you take a Z transform for this expression. So, when you take a Z transform for this is nothing but E of Z and here S of Z and here the delayed version. So, therefore, we will get Z polynomial. So, this is nothing but S of Z, if you take outside, this becomes 1 minus a k into Z power minus k or Z power minus I, right, where I varies from 1 to p. So, you will get this expression, and from this expression if you rearrange the terms, you can write E of Z by S of Z equals to A of Z, right. A of Z is nothing but this one, where this polynomial, right. Right here if you put E of Z by S of Z is nothing but A of Z, right. This A of Z is nothing but this one, this is the 1 minus a k into Z power minus a I into Z power minus I summation over I equals to 1 to p, right. So, this is the expression, and now if you write this if you want to examine this expression in the form of a system, we know that E of Z is nothing but the output, right, and S of Z is nothing but input, right. So, and then the corresponding transfer function is A of Z. So, the simple thing we can able to write this in the form of this one in the block diagram, right. A of Z is a transfer function. For this the input is S of Z, that is nothing but speech, and output will be my error in prediction, error in the signal, right. So, this way we can able to represent the system in the analysis phase, in the speech analysis phase, right. So, when you apply a linear prediction analysis for the analysis of a speech, you can see when you do this, here our ultimate goal is to minimize the error, right. So, when you try to minimize the error here, you can able to see that the transfer function of a system will be A of Z, and the input is the speech, and then we need to like predict the coefficients such a way that the error will be minimized. Here A of Z is nothing but a Z polynomial, right, where each term is multiplied by certain coefficient, right, and here our ultimate goal is nothing but given the speech signal, we need to estimate the coefficients such that the error will be minimized. So, that is the objective over here. So, here since we know that you can see this particular transfer function, right, A of Z, right, this is an algebra system, right, because you can see there is no denominator at all. So, therefore, here there is a polynomial, it is there in the numerator itself, denominator is not at all exist. So, therefore, you can view this as the algebra system and all, and if you try to see with the synthesis model, compare with the synthesis model, this filter is exactly the reverse or the reciprocal of the synthesis model, right, because in case of synthesis model our transfer function is 1 over A of Z, So, for that you have input is the excitation and your output is the speech, So, now in this model here you can see your input is the speech signal, output is the error signal, the output will be the error signal and all, right. So, that is the reason that you can see the transfer function also just flipped, Like earlier the transfer function is 1 over a of z, and now this transfer function is a of z, simply algebra system. So, if you want to analyze this system response here, like in the case of analysis phase, if you want to analyze the system response, this is, since it is algebra system, the system response will be something like this, right. Here these are the locations where the zeros are exist, that means the complex conjugates will occur here at this position, and at the roots of the polynomial the system response will be tend towards to 0. At the root locations the system response is pulling towards 0, because at root locations the expression leads to zeros, expression value leads to 0. So, that is the reason that here you can see this location here, here, here. So, these are the locations where the zeros exist, that means the root locations where zeros exist, and since it is a algebra system or only numerator polynomial exists, so therefore, at the root locations the system response will be pulled towards 0, right. So, therefore, there are known to be zeros of a system, and this is the algebra system. And if you look at here, this system, the filter offered by this system will be a of z algebra system, which is just inverse to the synthesis filter or a generating filter. So, because for a synthesis filter it is like 1 over a of z, right. So, but whereas here is a of z, so therefore, this is known to be also known to be inverse filter formulation, and this, by using this inverse filter formulation, you can able to compute or you can able to estimate the coefficients of the polynomial, or a case you can able to, or whatever this a is, they are going to be linear prediction coefficients. So, these things you can able to estimate by using the inverse filter formulation, because you know the speech signal, right, and you need to find out these coefficients such a way that by using these coefficients you can able to, later on you can able to generate the speech back, right. So, you need to find out these coefficients such a way that, right, from the given speech frame you need to find out the set of coefficients where the error will be, the overall error will be minimum, the overall error should be minimum, right. So, that way here the estimation of these coefficients from the speech frame, it is nothing but that we will do that, it is nothing but estimation of these prediction coefficients, estimation of this linear prediction coefficients for every frame, for every frame. So, and if you see the response, this is the response of this a of z, we will see that how do we estimate the linear prediction coefficients for a given signal and all, right, for the given frame, because we cannot compute the linear prediction coefficients for the entire speech utterance, because since we know that the speech utterance is a time varying signal, right, because the speech utterance consists of multiple sounds. So, each sound has its unique characteristics. So, therefore, a speech signal of 1 second or 2 seconds, it consists of multiple sounds. So, therefore, we cannot apply the linear prediction analysis for the entire speech utterance, right. So, that is the reason that we are applying the speech this linear prediction analysis at a smaller frames, right, at a smaller frames of size 20 milliseconds or 30 milliseconds with the overlap, right, with the overlap of 5 milliseconds, right, that shift of 5 milliseconds. So, therefore, for every 5 milliseconds we have a speech frame, right. So, now we can see how do we estimate the linear prediction coefficients, how do you compute the linear prediction coefficients for a given speech frame. For that, what we need to do, our objective is that we need to minimize the error, for a given speech frame. We need to estimate the LPCs or the linear prediction coefficients with the objective of minimizing the error, right. So, that way if you look at here, your S hat of n is nothing but the predicted speech signal, and that you can able to do it from its previous samples, from the previous samples a case, right. So, from the previous samples we will try to estimate, right, we will try to estimate the predicted the sample, right, and for that because since we know the previous samples, the only thing that we need to know is that a case, right, we need to know is the a case. These a case are nothing but the scaling factors associated to the previous samples, right. So these things we need to be estimated, and here we need to estimate these ones with respect to, right, with respect to the minimization of error, because S of n is actual speech signal, we know that actual speech signal we know, right, and then we will try to find out these AKs such a way that this predicted speech signal is very close to the actual speech signal, then in that case the error is minimum, right. So, the error in the prediction of nth sample can be written as E of n equals to S of n minus S hat of n. So, that we have seen, right. So, S of n, S hat of n is nothing but the predicted nth sample from the history, from the previous p samples. So, that way here by using this expression you can able to compute, or you can able to realize the predicted nth sample. The difference between these two give you the error in the nth sample. But our objective is that for a given speech frame or a speech segment of 20 milliseconds or 30 milliseconds, like the overall error whatever is there, that has to be minimized. It is not that our objective is to, like, for a given instance and all, like on the whole for a given speech frame, right, the overall error has to be minimized. So, whereas E of n is nothing but the error that is associated to nth sample in the prediction process, right. So, the overall error is nothing but E of n is the error associated to nth sample. Likewise, we have some, like in case of 20 milliseconds we have 200 samples will be there. So, this capital N becomes 200, right. If it is a 30 milliseconds with a 10 kilohertz sampling rate, then this n becomes 300. So, that way this n is nothing but the number of samples in a frame, right. So, for each sample there will be some error association with that, some error will be associated with that because of the prediction, right. So, therefore, here the squared error is nothing but E of n square over all samples n equals to 1 to n equals to 1 to n. So, this gives you the total squared error, the total squared error. And now, what is E of n? E of n is nothing but S of n minus S hat of n, or the prediction, right. So, this is the one, and now E of n square is nothing but if you take the square of this one, that gives you E of n square. So, this is the squared error. So, my objective here is that I need to minimize this error, overall error, or the sum error, the error over the entire frame has to be minimized, right. How do I do that? Here in the minimization, what here we have anyway the speech samples are available. So, the only things that can be controlled to minimize the error will be these scaling factors, right. Otherwise, this S of n is known, that is the speech samples, right, and S of n minus k is also a speech sample, but it is a preceding samples. So, here in this expression, to control the error, the only thing that can be estimated or can be optimized will be these scaling factors. We need to find out the optimal scaling factors for the entire frame such that this overall error will be minimized. So, for that the only thing that I can able to estimate, I can able to control the error will be based on choosing or based on determining these coefficients in an optimal way, these coefficients. So, we know that since it is a squared error, we can able to know that actually we can able to compute the optimal coefficients. For doing that, what we can do, we can have if we take a derivative of this squared error with respect to these coefficients, and equate to 0, then by solving that we can able to find out what is the optimal value of a case, so that the error can be minimized, right. We have error, and then for minimization of error, right, or minimization or maximization of error, what we can do is that take a derivative of it, first derivative, and then equate to 0. So, if you want to take a derivative with respect to here a case, so therefore, here you can say for optimal values of a case, what you need to do is that we need to take a derivative of E with respect to a k, and here how many a k's are there? We have k varies from 1 to p, there are p coefficients are there. So, therefore, here whatever the error expression is there, so we need to take a derivative of this expression with respect to each of these AKs. There are such P coefficients are there. So, therefore, we need to take a derivative and equate to 0 with respect to each of the AK. So, likewise, that means there are like P coefficients are there. So, therefore, we will get a P equations. We will get the P equations, because with respect to each AK you are taking a derivative and equating to 0. So, we will get a P equation, because there are P coefficients are there, like because we have P coefficients with which we will take a history and then we are estimating the sample. So, there are P coefficients are there. So, with respect to each coefficient you are taking a derivative and equate to 0. Then with this we have some P equations are there, right. So, when you solve those P equations, then we will get these AKs, we will get the optimal AKs. So, now if you apply a derivative, it is nothing but just you expand this, right. It is a simple mathematical continuation steps. You need to expand this and try to take a derivative with respect to AK, right. When you try to take a derivative with respect to AK, this S of n square and all, this is a constant term. So, that leads to 0. So, that way if you apply a derivative, then you will come up with this one expression. You will come up with this expression like summation of k equals to 1 to p AK, then again summation over n. You can see there are two summations. Summation over n is nothing but number of samples in a frame, and summation over k is nothing but, here k refers to number of coefficients, number of coefficients, number of the previous samples that we are considering for prediction, right. There are two summations with two different indices, right. So, that way here you can see this is nothing but AK multiplied by summation over n S of n minus k into S of n minus I equals to this one, summation over n S of n into S of n minus I, where here I is varying from 1 to p, I is varying from 1 to p. It means that here if you look at here, you can have the P expression, but if you keep I equals to 1, we have one expression, I equals to 2, I equals to 3 up to P, we have a P expressions. So, it means that we have the P equations were there, we have the P equations, and if we solve these P equations, we will get the P unknowns. What are the unknowns here? AKs are the unknowns, otherwise this S of n minus k, S of n minus I, S of n, S of n minus I, these are known, because that is a speech signal is available for us. The only thing that is not known is AKs. So, if we solve these P equations and there are P unknowns, if you solve it, then you can get the optimal values of AKs, and those are nothing but your linear prediction coefficients, right. They are not nothing but the prediction coefficients, right. And now, if you look at these expression, if you look at this S of n minus k into S of n minus I, S of n into S of n minus I. So, these are nothing but they are related to your autocorrelation, because it is same signal shifted by different amounts, and here same signal, one is not shifted, other is shifted by some amount. So, therefore, here these expressions are very much close to or very much related to the autocorrelation expression. So, now by plugging those autocorrelation definition over here, you can able to see that the same expression, whatever the earlier expression, can be written as AK into R of I minus k, right, summation over k equals to 1 to p equals to R of I, equals to R of I, right. Right, that is the expression, because whatever you get earlier one, you can see like here you can see this one, this is S of n into S of n minus nothing but a signal and a shifted version, we are multiplying that, right. So, that way you will get R of I, that means correlation at ith shift, correlation at ith shift, right. So, likewise here also, right. So, then if you plug in those based on the definition of autocorrelation, you will get the expression something like this. So, summation over k equals to 1 to p AK into R of I minus k, right, equals to R of I, where I varies from 1 to p. And now, this one, if you can write it here in the form of the matrix notation, you can see here k is varying from 1 to p and I is varying from 1 to p, right. I is also varying from 1 to p and k is also varying from 1 to p. So, with that, this product ak into r of I minus k. If you plug in both the values simultaneously, k and I together, you will get here this particular expression, right? Because here if you put k equals to different values 1 to p, you will get this particular vector a1, a2, a3, ap, a column vector. And here for r of I minus k, if you plug in different values of k for each value of I, because each time the k will be applied over here for each value of I. When I equals to 1, here you can see, and if you apply different values of k, you will get the coefficients, you will get autocorrelation coefficients, autocorrelation values corresponds to maybe the first row, right, first row. And similarly for I equals to 2, when you do it, you will get a second row. For I equals to p, you will get the last row. So that way you can able to write this expression in the form of this matrix notation. And anyway, this r of I for different values of I equals to 1 to p will get a column vector. This is just similar to a of k, right, for different values of k. Here there is no influence of I, so therefore you will get only one column vector. But here r of I minus k, it is influenced by both k and p, because here for every value of I, like here the k will take p values. So therefore here this r of I minus k will give you the p by p matrix. This is nothing but this one, this p by p matrix, right. You can see 0 to p minus 1 and 0 to p minus 1, right. In each column we have p elements, and in each row we have a p element. So therefore this matrix is a p by p matrix, p cross p, and this is a column matrix with p elements, and this is also a column matrix with p elements. And now here these autocorrelation values you can able to compute, right, because we know the speech signal, speech frame, we know that, we have that. So using a speech frame, you can able to compute this r of 0, r of 1, r of 2, all these things you can able to compute, right. Here you need to compute only the up to p, like r0 to rp, r0 to rp. We know that how to compute these autocorrelation values, right. We know how to compute the autocorrelation values. Simple thing, like r of I is nothing but what is this r of I? S of n multiplied by s of n minus I, right. What is suppose you have a signal, and if you shift by like I samples, then afterwards if you try to see the what is the overlap, and then take the signal, the overlap, the sample multiplications and sum of them, that gives you the autocorrelation value at ith shift, right. So likewise you have to calculate the autocorrelation values for, right, for autocorrelation values for, like you can see up to p, like r of 0 to r of p minus 1 you have to calculate for this, and here r1 to rp you have to calculate, right, because the speech signal is available, you can able to calculate. So once we have done that, so here our objective is that you have to find out this a1 to ap, like these coefficients. So these are the scaling factors, are also to be prediction coefficients, right, because they are like associated with for predicting the sample. So these coefficients are used as the scaling factors for the previous samples. That means each previous sample is multiplied by one of these coefficients, and then taking the sum over all of them. So that gives you the predicted sample, right, from the history, from the previous samples. So for estimation of this, or for computing this set of values, these p values, then we have to solve this expression. So for solving this, since by without using anything in a crude way, like using a matrix algebra, you can able to solve it, right. So a1, a2, a3, p, nothing but this divided by this one. So that gives you this, you can able to solve it. But that requires more computations, because you require that for doing that you need to have number of computations that are required will be p cube by 3 plus O of p square operations are required for computing using a Gauss reduction method. Using a Gauss reduction method, right, if you solve this for these p values, you can see that the complexity that is involved will be p cube by 3 plus O of p square operations are required for computation of that. And then for managing that, we need to have p square storage elements are required, because the p square means this entire matrix has to be stored. So therefore p square storage elements are required, right. And then by using some other decomposition method and all, you can able to further reduce the number of operations by p cube by 6 plus O of p square, right, and the storage requirement is also reduced to p square by 2, because that is known that, because since it is you can see the matrix here with respect to diagonal, like whatever is there in the upper diagonal, you can also see the lower diagonal also, right, and this kind of a matrix are known to be Toeplitz matrix, like Toeplitz matrix. Since it is a Toeplitz matrix, then you do not need to store all elements, because if you store half of them, that is good enough, p square by 2. And since it is a Toeplitz matrix, and you can see the properties of Toeplitz matrix and all, you can use the recursion for solving these p equations. You can use the recursion and all, and there is a well known recursion known to be Levinson, Robinson, and then afterwards a Durbin recursion. So, by applying a recursion, you can able to solve these you can able to compute these LP coefficients, right, using this like a p square plus O of p, that means for the linear complexity, linear order, right. P square plus O of p is the complexity, is the number of computations that are, number of operations that are required to compute the this linear prediction coefficients. So, if you use the, other than this, if you do not use recursion, if you use the normal approaches, the number of operations that are required will be O of p square, that means O of n square complexity, whereas here it is a linear O of p, like there is a much reduction in the number of computations that are required, and at the same time you can see that the storage elements that are required also will be reduced to 2p. Here you can see it requires p square by 2, but here the number of elements that are required for storage is also, memory storage is requirement also 2p. So, that way by using the effective recursion algorithms and all, you can able to perform this computation very effectively, right. So, that way the computationally it is not that much complex, right. So, you can see, because for every frame, right, you can able to compute this LP coefficients with this complexity, like just order p. Order p is nothing, because the number of coefficients per frame will be around 15 maximum, right, around 15, 10 to 15. So, therefore, you can able to compute with order p operations. But before doing that, like before solving that, you need to compute these autocorrelation values, right, p autocorrelation values you have to compute, right, because R0, R1 to RP, like R0 to RP, right, this p or p plus 1 autocorrelation values have to be computed. But again, this p autocorrelation values computation also not very cumbersome, right, compared to pitch estimation. And here in the case of LP analysis, you need to compute these autocorrelation values, only p autocorrelation values need to be computed, right. It is not that much heavy for a particular frame, because why I am saying is that this is, all these calculations or computations are referred to one particular frame, and suppose if you want to perform these for a speech signal, it means that for every frame you need to perform these calculations, this many computations are required. That means for every frame you need to compute p autocorrelation values, and afterwards for solving these expression, for computing these LP coefficients, so you need to perform this one, like you need to perform p square plus order p computations are required, operations are required and all, operations are required for every frame. So, in case of 1 second of a speech, we have such 200 frames will be there, right, 200 frames will be there. So, try to imagine how many computations that are required to perform the LP analysis and all. So, that time, no, because of this, you can see by using this Durbin's recursion and all, you can able to perform this with a normal linear order. Linear order is not very expensive and all, computationally expensive, right. So, this way you can able to compute the linear prediction coefficients for every speech frame and all. So, how we are doing for the analysis frame, in the analysis phase, where we are trying to estimate the error and we will try to minimize the error, and in the process we have p normal equations are there, like, and by solving the normal equations you can able to get these linear prediction coefficients. right. And this is the one where, yeah, if you perform a linear prediction analysis, right, and in the process of computing the linear prediction coefficients, our aim is to minimize the error. Our aim is to minimize the overall error and all. And if you analyze this error for a speech signal, right, on a speech signal, so we know that the speech consists of voiced speech and unvoiced speech. In case of voiced speech, the samples are correlated, and in case of unvoiced speech, the samples are not correlated, right. And if you try to analyze the error, the prediction error in a speech, means we need to analyze with respect to voiced speech how the prediction error will be there, and in case of unvoiced speech how the prediction error used to be. So, for performing that analysis here, we just try to compute the error in the prediction. So, this is the E of n is nothing but error in prediction of nth sample, and for a total frame the total error will be E of n square over the n over all samples, and that you can able to do it by this way, by computing this one, like S of n minus the actual minus prediction square, that gives you the squared error of the particular sample, and the summation over all the samples give you the sum of the squared error and all. And if you look at this sum of the squared error, and then if you try to just same thing, whatever is here, I just substituted appropriate expressions corresponds to that, because this predicted sample is nothing but predicted from the p samples. So, that is nothing but a k into some s of n minus k, and then substitution of that, and then expanding this square, right, you will get the 3 terms, like, and then you will get these terms, and then here we can use the result of the normal equations. We can use the result of normal equations, whatever we got in the process of computing LPCs, right, we get this expression, right, in the this expression we got, and this result, if you use it here in this in the evaluation of error, then this error expression can be minimized to, or can be obtained, can be reduced to this one, S of n square over the summation n minus summation of a k with respect to k into S of n into S of n minus k. And now based on the definition of autocorrelation expressions, if you substitute the corresponding autocorrelation definition here, S of n square is nothing but R of 0, because S of n square is nothing but S of n multiplied by S of n. So, autocorrelation is nothing but signal and it is a shifted version, and here the shift equals to 0. So, we can say that autocorrelation at 0 shift, autocorrelation at 0 shift, this is this term, and this term is nothing but autocorrelation with the k shift, that is nothing but R of k and summation over k. So, this way we can able to compute the expression for error in terms of the autocorrelation coefficients R of 0 minus a k into R of k, where k varies from 1 to p. This is the expression. And now by using this expression we can able to explain how the error is varying as you increase the value of p, because here the p is nothing but number of the past samples that are considered for prediction and all. As you increase the value of p, you can see that the error will be decreased, and that you can able to analyze by using this expression itself, right. Okay. So, we will stop here at this point, and the next class we will continue that. Okay. Yeah, thank you.